Millions of kilometers above our heads, in the dark silence of space, a golden eye remains open. A machine that was launched as humanity's greatest hope. In December 2021, when the James Webb Space Telescope, or JWST, departed toward the depths of space, scientists around the world erupted in celebration. Everyone believed we would finally witness that first moment of the Big Bang, the very instant where our existence began. But over the past few years, the data this telescope has sent back has replaced joy with fear in the hearts of scientists. Out there in that deep darkness, something was discovered that appears to break all the rules of our physics. We thought we would see the universe's childhood, tiny stars and galaxies in the process of formation. But Webb found monsters instead. Things that should not have been there at all. What if I told you that our universe is far older than we understand? What if the Big Bang did not happen the way we have always believed? Today we will embark on that unknown journey where even light hesitates to tread. Let us walk alongside JWST to confront a truth that perhaps we were never meant to know. The Webb telescope is essentially a time machine. Light takes time to travel. So when we look far into space, we are actually peering into the past. Scientists' standard model of cosmology stated that immediately after the Big Bang, the universe was like a hot soup. Matter needed to cool down and coalesce, and it should have taken hundreds of millions of years for gravity to gather enough material to form stars. We expected to find small, faint, and lightweight galaxies in the early universe, what we know as baby galaxies. But when Webb looked back 13 billion years, it did not find babies. It found fully grown adults. Webb observed galaxies that existed only 300 to 500 million years after the Big Bang, yet their size and mass were as vast as our own Milky Way galaxy. These discoveries were given the name universe breakers. According to the mathematics, that much matter could not have accumulated in one place in such a short time. If the laws of physics were the same then as they are now, the existence of these galaxies in that era was impossible. This discovery shook the very foundation of our Big Bang theory. Either the universe was far older than we estimated, or something happened in the beginning that we have no idea about. This forces us to think, are we living inside a wrong model? The story does not end here. It goes deeper. There's a theory that sounds like something from a horror movie script, but Webb's data suggests it might actually be true. We are talking about dark stars. We all know that stars like our sun burn through nuclear fusion, giving off light and heat. But in the beginning of the universe, when matter was extremely dense, scientists believed the first stars would have been made not from hydrogen, but from dark matter. Dark matter is that mysterious substance we cannot see, yet it makes up the vast majority of the universe. According to theory, in the beginning, dark matter particles collided with each other and gave birth to these dark stars. These would be completely different from normal stars. They would be so massive in size that our entire solar system could fit inside them. They would emit more heat and infrared energy than visible light. Webb captured certain objects, like JWST 130, that appeared to be galaxies. But some experts suggested that what looked like a galaxy could actually be a single colossal dark star, a star that survives not on light, but on the power of darkness. It is terrifying to think that in the universe's infancy, such monsters ruled, capable of challenging the light of an entire galaxy all by themselves. The idea that the universe's childhood was dominated not by gentle starlight, but by these massive dark entities fundamentally changes how we think about cosmic evolution. These dark stars, if they truly existed, would have been unlike anything we see today. Their energy would come from the annihilation of dark matter particles within their cores, creating an entirely different kind of stellar object. But temperatures, pressures, and physics governing these objects would be so alien that our current models barely scratch the surface of understanding them. When we consider the implications of dark stars, we must confront an uncomfortable truth about our understanding of stellar evolution. Every textbook, every model, every simulation we have created about how stars form and evolve is based on observations of our current universe. But what if the early universe played by completely different rules? What if the first billion years of cosmic history were governed by physics we have yet to fully comprehend? The detection of these anomalous objects by Webb forces us to reconsider everything. Scientists are now going back to their calculations, rewriting equations, and developing new models that can account for these observations. Some researchers suggest that perhaps our understanding of dark matter itself needs revision. Maybe dark matter is not just one type of particle, but a whole spectrum of particles with different properties and behaviors. Perhaps in the dense early universe, these particles interacted in ways they no longer do and are more spread out. Modern cosmos black holes are the monsters of space that even swallow light. We believe that black holes formed after stars died and gradually grew larger over time. It should take billions of years for a supermassive black hole to form. But Webb discovered black holes at the centers of galaxies like GNZ11 that existed shortly after the universe formed, and their size equaled millions of suns. The question arises, how did such a massive monster come into existence so quickly? What did it consume to become so large? Scientists find the answer frightening. One possibility is that these black holes formed through direct collapse. Instead of a cloud forming a star, an entire gas cloud collapsed upon itself and directly became a well of death without any star dying first. A hungry monster was born directly, without any stellar death preceding it. These black holes were so ravenous that they began consuming all the gas in the early universe. The thought that the universe began not with creation, but with consumption and destruction, shatters our romanticized cosmic view. Webb showed us that the universe is not a peaceful place, but a violent battlefield, where large monsters have been devouring smaller things. From the very beginning, the formation of these supermassive black holes in the early universe presents one, the most significant challenges to modern astrophysics. Our current models simply cannot explain how black holes, millions of times more massive than our sun, could have formed in just a few 100 million years. Traditional stellar evolution theory tells us that black holes form when massive stars exhaust their nuclear fuel and collapse. These stellar mass black holes, typically ranging from a few to a few dozen times the mass of the sun, then must grow by accreting matter or merging with other black holes. This process is inherently slow. Even under the most optimistic assumptions about accretion rates and merger frequencies, it should take billions of years, not hundreds of millions, to grow a supermassive black hole. Yet there they are, plain as day in Webb's observations. Massive black holes, actively feeding on their surroundings, already dominating the centers of young galaxies when the universe was barely out of its infancy. Some of these monsters were so active that they would have been visible as quasars, shining brighter than billions of stars combined, while the universe was still in what we considered its childhood. The existence of these objects suggests several disturbing possibilities. Perhaps the direct collapse scenario is correct, and under the right conditions, massive clouds of gas can collapse directly into black holes without forming stars first. This would require very specific environmental conditions, possibly only achievable in the early universe. Or perhaps black holes were somehow seeded during the Big Bang itself, with primordial black holes forming directly from density fluctuations in the first. Moments of cosmic history. Another possibility that keeps some cosmologists awake at night is that perhaps there is something fundamentally wrong with our understanding of gravity at these extreme scales and conditions. Maybe Einstein's general relativity, which has passed every test we have thrown at it so far, breaks down or behaves differently in the extreme environment of the early universe. This would be a revolutionary discovery, forcing us to rewrite not just cosmology, but fundamental physics. The biggest fear is not of the unknown, but of confusion. When you realize that your basic knowledge is wrong, that is when true discomfort sets in. Physics is currently experiencing a crisis called the Hubble tension. Webb has poured fuel on this fire. Hubble tension refers to the rate at which the universe is expanding. When we measure the expansion using observations of the old universe, we get one speed. When we measure it using observations of the distant past universe, we get a different speed. Scientists hoped that James Webb would arrive, provide accurate data, and this discrepancy would disappear. Everyone thought perhaps there was some error in our calculations, but the data Webb provided confirmed that our measurements are correct. The universe really does appear to be expanding at two different rates, depending on how we measure it. This means something very significant is missing from our model of the universe. Some unknown force is pushing the universe. Is there a flaw in Einstein's theory? Even in the 21st century, we do not know at what speed the universe is growing. This feels like a slap to our scientific arrogance. The Hubble tension is not just a minor discrepancy or measurement error. It represents a fundamental crack in our understanding of cosmology. Different methods of measuring the universe's expansion rate give results that disagree by about 9%. That might not sound like much, but in cosmology, it is enormous. It is the difference between a universe that is 13.7 billion years old and one that is 12.5 billion years old. It is the difference between different cosmic histories, different futures, and potentially different physics. One method of measuring the expansion rate, called the Hubble constant, involves looking at distant supernovae and using them as standard candles to measure cosmic distances. This method gives us one value. Another method involves looking at the cosmic rho wave background radiation, the afterglow of the Big Bang, and using its properties to calculate what the expansion rate should be today. This gives us a different value. For years, scientists assumed that one or both methods had some systematic error that would eventually be identified and corrected. But as measurements have become more precise, the discrepancy has not gone away. It has become more pronounced and more statistically significant. Webb's contribution to this crisis has been to provide even more precise measurements, and unfortunately, these measurements have confirmed that the discrepancy is real. The universe, according to these observations, is genuinely behaving in ways we do not understand. Some scientists propose that there must be some form of dark energy or dark radiation that we have not accounted for. Others suggest that perhaps the universe's expansion is not uniform, that different regions of space might be expanding at different rates. More radical proposals suggest that maybe we need to modify our theory of gravity itself, that Einstein's equations need correction when applied. Over cosmic distances and timescales, the implications of the Hubble tension extend far beyond academic debates. If we do not understand how fast the universe is expanding, then we do not really understand the universe at all. We do not know its true age, we do not know its ultimate fate, and we cannot trust our models of cosmic evolution. Every calculation about the early universe, about dark energy, about the formation of structure, becomes uncertain. It is as if we have been reading a history book for decades, confident we understood the story, only to discover that we have been reading it upside down. The universe, it seems, has been hiding its true nature from us. And every attempt to pin it down reveals new layers of mystery. When we look through a telescope into space, somewhere in a corner of our hearts, we hope that someone out there is looking back at us. One of Webb's major missions is to scan the atmospheres of exoplanets to find signs of life. Webb has found traces of water and carbon molecules on planets like K218b, indicating the possibility of an ocean world. A molecule called dimethyl sulfide was detected there, which on Earth is only produced by living organisms. If this is confirmed, it would be the biggest proof of life in the universe. But the other side of this is extremely frightening. When Webb studied some planets in the TRAPPIST-1 system, it discovered that some of them have no atmosphere at all. They are spinning around their star like barren rocks. This reminds us how rare and fragile life is. And if life did exist on K218b, what guarantee is there that it would be friendly? What guarantee is there that it is still alive? It is possible that the signals we are detecting belong to a civilization that ended millions of years ago. and we are merely searching through their ashes and smoke. The great silence becomes even deeper when we realize we might not be alone. But those we are searching for might also pose a danger to us. The search for extraterrestrial life has always been filled with hope and optimism. We imagine making contact with an advanced civilization, sharing knowledge, learning from each other, perhaps even forming some kind of cosmic community. Popular culture has prepared us for friendly aliens, wise mentors from the stars who will guide us to a brighter future. But Webb's observations force us to confront a darker possibility. What if life in the universe is common, but survival is not? What if the universe is filled with the remains of civilizations that rose and fell, that reached for the stars and then vanished, leaving behind only faint chemical signatures in the atmospheres of dead worlds? The detection of potential biosignatures on distant exoplanets is thrilling, but it also raises disturbing questions. If we do detect life, what will we find? Will it be microbial slime clinging to existence in some extreme environment? Will it be complex ecosystems that have evolved along completely different paths from anything on Earth? Or will it be something so alien, so fundamentally different from our conception of life that we struggle even to recognize it? And if intelligent life exists elsewhere, why has it not contacted us? The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for them, becomes more pressing with every new exoplanet we discover. Where is everybody? One possibility, known as the Great Filter, suggests that there is some barrier, some challenge or catastrophe that prevents civilizations from surviving long enough to become spacefaring. This filter could be in our past, something that was extraordinarily unlikely about the origin of life or the evolution of intelligence, which would mean we are extraordinarily lucky to have made it this far. Or the filter could be in our future, some disaster or challenge that awaits all civilizations as they advance, which would mean that our own survival is far from guaranteed. Webb's discovery of worlds that once had atmospheres but lost them, of ocean worlds that might harbor life beneath their surfaces, of the sheer violence and hostility of space, all of this suggests that the universe is not a gentle place. Survival is hard. Persistence is rare. And perhaps, just perhaps, we are alone after all, or at least we are alone in this small corner of space and time. Looking at Webb's pictures, we often say, wow, because we find them beautiful. But the truth behind those colors is often quite disturbing. Webb looked again at the pillars of creation and captured the violent birth of new stars behind those dust clouds. But it also detected polycyclic aromatic hydrocarbons in space. These are the same chemicals found in cancer-causing pollution on Earth. These are the building blocks of the universe. But they tell us that space is a toxic, radioactive, and deadly place. We thought that space was an empty place, but Webb showed that space is full, filled with dust, radiation, and the debris of broken stars. It is like a graveyard where fragments of old worlds are floating everywhere. When we look at those colorful pictures, we are actually looking at a dance of death and destruction that has been ongoing for billions of years. The romanticized vision of space as a pristine, peaceful void is shattered by Webb's observations. Space is not empty. It is filled with matter in various states of decay and transformation. The beautiful nebulae we admire are often the remnants of stellar explosions, the death throes of massive stars that tore themselves apart in supernova. The intricate structures we see in these images are sculpted by intense radiation and stellar winds, forces powerful enough to strip atmospheres from planets and sterilize any life that might exist. The colors that make these images so striking are not natural. They are false colors assigned to different wavelengths of light that our eyes cannot see. In reality, most of space would appear dark to human eyes, illuminated only by the faint glow of distant stars and the occasional flash of cosmic violence. Webb has revealed that the interstellar medium, the space between stars, is far from empty. It is filled with complex organic molecules, the chemical building blocks of life, but also with radiation and particles moving at nearly the speed of light. These cosmic rays can tear apart DNA, making space incredibly hostile to life as we know it. The gas and dust clouds that give birth to stars are also cesspools of toxic chemistry, where temperatures range from near absolute zero to millions of degrees, where pressures are either nearly zero or crushing, where radiation can strip electrons from atoms and tear molecules apart. This is the environment from which planets and life must emerge. It is a miracle that anything survives at all. The detection of polycyclic aromatic hydrocarbons, or PAHs, throughout the universe is particularly telling. On Earth, these molecules are associated with incomplete combustion, with pollution and environmental damage. They are known carcinogens. Yet in space, they are everywhere, making up a significant fraction of all the carbon in the universe. They form in the outflows of dying stars and are scattered throughout the cosmos. Future astronauts venturing beyond Earth's protective magnetic field and atmosphere will have to contend with this toxic environment. The dust that looks so beautiful in Webb's images would be deadly to breathe. The radiation that creates those stunning colors would be deadly to biological tissue. Space, for all its beauty, is trying to kill us at every turn. Asterisk, let us dig a little deeper into this impossible galaxy business. There is a special galaxy called CEER 93316 when Webb first observed it. The data indicated it was from just 235 million years after the Big Bang. This was record-breaking, but scientists could not believe it. This data was based on what is called photometric redshift, an estimate based on colors. Later, when a proper scan was conducted, it was discovered that this galaxy was not actually that old. Instead, due to dust and hot gas, it was masquerading as being much older. This incident gave scientists some relief, but also created a new fear. The fear of impossibly things in space are not what they appear to be. In Webb's data, there are still dozens of galaxies that are confirmed to be at high redshift. Their existence remains a puzzle. This teaches us that the universe is like a magician showing us illusions. Is what we see real, or is it just a play of light that is playing with us from billions of light years away? Every time we think we have caught the universe, it slips away. This cosmic game of hide and seek is very exhausting for our minds. The photometric redshift technique relies on analyzing the light from distant objects across multiple wavelengths. By comparing how much light is received at different wavelengths, astronomers can estimate how much that light has been stretched by the expansion of the universe, which tells them how far away and how old the object is. It is a powerful technique, but it is also prone to errors. Dust can absorb and scatter light, making objects appear redder than they should be. This can fool the analysis into thinking an object is much more distant than it really is. Asterisk, the case of CEER 93316 was a wake-up call. It showed that we need to be careful about making bold claims based on photometric redshifts alone. Spectroscopic confirmation, where the light is spread out into a spectrum and individual spectral lines are identified and measured, is much more reliable but also more time-consuming. Webb simply cannot obtain spectroscopy for every interesting object it finds. There are too many, and telescope time is limited, so astronomers must make difficult choices about which objects to follow up in detail. The fear is that among all the candidates for extremely distant galaxies, some are genuine, representing objects from the very early universe that challenge our models, while others are imposters, much closer objects masquerading as distant ones. Sorting the real from the fake is a painstaking process. Asterisk, but even accounting for imposters, there remain many galaxies in Webb's data that appear to be genuinely from the very early universe and genuinely too massive, too evolved, too structured for their age. These are the ones that keep cosmologists awake at night. They represent a fundamental challenge to our understanding of how structure forms in the universe. According to our models, the early universe should have been relatively smooth, with only tiny fluctuations in density. Over time, gravity would amplify these fluctuations, pulling matter together to form the first stars, then the first galaxies. This process should be gradual. Yet, Webb is showing us galaxies that appear to have formed almost instantly on cosmic timescales, as if the universe somehow fast-forwarded through the early stages of galaxy formation. How is this possible? What are we missing? These questions drive the current revolution in cosmology, as scientists scramble to modify their theories to account for Webb's shocking discoveries. Asterisk. Now, let us open those frightening chapters that scientists often keep hidden from the general public because they completely destroy our comfort zone regarding existence. Earth revolves around the sun. The sun revolves around the center of the galaxy. But Webb and other deep space surveys have shed light on a reality that is no less than cosmic horror. Our galaxy, the Milky Way, and millions of other galaxies around us are all flowing in a certain direction. We are all drifting toward something. This mysterious place has been named the Great Attractor. It is not a black hole because a black hole cannot be large enough to pull millions of galaxies toward it. It is a gravitational monster sitting at the center of the Laniakea supercluster. Asterisk when Webb looked beyond the dust clouds in that direction. It found a gathering of galaxies, a scene like a graveyard where galaxies are colliding with each other and destroying one another. Imagine we are moving toward that place at millions of kilometers per hour. We do not know what will happen to us when we get there. Some theories suggest that time stops there. Others say that matter is completely crushed there. Webb's data shows that this attractor could be a drainage point in the structure of our universe, where matter exits the universe or falls into another dimension. The Great Attractor is not a single object, but a region of space with extraordinarily high mass concentration. It lies roughly 150 to 250 million light years away, hidden behind the galactic plane, where dust from our own Milky Way obscures our view. Despite this obscurity, we can detect its presence through its gravitational effects on surrounding galaxies and galaxy clusters. Asterisk our local group of galaxies, which includes the Milky Way and Andromeda, is moving toward the Great Attractor at about 600 kilometers per second. But it gets stranger. The Great Attractor itself is not the final destination. It too is being pulled toward an even larger structure called the Shapley supercluster. We are part of a cosmic flow, a vast river of galaxies streaming through space toward some distant, massive concentration of matter. This flow extends across hundreds of millions of light years and involves tens of thousands of galaxies, all moving together like leaves in a cosmic current. The realization that we are not stationary, that our galaxy and our local group are rushing through space at incredible speeds toward some distant destination, is both humbling and terrifying. Asterisk, what awaits us there? Will we collide with other galaxies? Will the gravitational forces tear our galaxy apart? Will the increased density of matter in that region lead to more frequent stellar collisions and supernova? Or will nothing particularly dramatic happen, with the process unfolding so slowly over such vast timescales that the sun will have long since died before we arrive? The truth is, we do not know. What we do know is that the universe is not static. Everything is in motion, flowing, falling, colliding. The peaceful night sky we see is an illusion. We are hurtling through space on a journey we did not choose, toward a destination we cannot fully understand, and there is nothing we can do to stop it. Asterisk, when we imagine alien life, we always picture a sun. But Webb looked inside the Orion Nebula and saw something that challenged the definition of life. It observed jumbos, Jupiter-mass binary objects. These are planets that do not orbit any star. They are also known as rogue planets. In the deep darkness of space, where temperatures drop below negative 200 degrees Celsius, these planets drift alone. But the fear is not that they exist there. The fear is that their numbers are far greater than we estimated. Webb's observations suggest that there may be more of these orphan planets in our galaxy. Then there are stars. Asterisk. Now imagine a world where the sun never rises, where it is always night. But Webb's infrared sensors showed that some of these planets are warm inside. Volcanoes are erupting there. Tectonic plates are moving there. This could mean that life might exist there. A civilization born in darkness. raised in darkness. For them, light would be a myth or perhaps even a threat. If we ever went there, how would they perceive the light from our flashlights? Perhaps as an attack. Webb has shown us that most of the universe lives not in light but in darkness. We light dwellers are just a small minority. The real universe exists on those dark planets. The discovery of rogue planets in such large numbers forces us to reconsider what we mean by a habitable world. We have always assumed that life requires a star, that the energy from stellar fusion is necessary to drive the chemical reactions that underpin biology. But what if we are wrong? What if life can exist using the internal heat of a planet, powered by radioactive decay or tidal heating or leftover heat from formation? Rogue planets, ejected from their original solar systems during the chaotic early days of planetary formation, might retain enough internal heat to maintain liquid water beneath thick ice shells. These subsurface oceans, completely isolated from any external light source, could potentially harbor life. Asterisk on Earth. We have found life in the deepest, darkest parts of the ocean, clustered around hydrothermal vents where no sunlight ever reaches. These ecosystems are powered entirely by chemical energy, by the reactions between hot mineral-rich water and the cold ocean. If life can thrive there, why not on a rogue planet with a subsurface ocean heated by its own core? Such life would be completely alien to us. It would have evolved in total darkness, with no concept of light or day or seasons. Its biology, its chemistry, perhaps even its physics would be adapted to conditions we can barely imagine. And if such life could become intelligent, if it could develop technology and civilization, it would be so fundamentally different from us that communication might be impossible. Asterisk, the implications are staggering. If rogue planets outnumber stars, and if even a small fraction of them could harbor life, then the universe might be teeming with living worlds, most of which we will never detect because they emit no light. We have been searching for life by looking for Earth-like planets in the habitable zones of stars. But perhaps the majority of life exists elsewhere, in the darkness between stars, on worlds we can barely see and would never think to examine. This realization expands the possibilities for life in the universe while simultaneously making the search even more difficult. How do you find a dark planet against the darkness of space? How do you distinguish a living world from a dead rock when both are equally invisible? Webb's infrared vision gives us a chance, but it is a small one. The universe, it seems, keeps its secrets well hidden. Asterisk. The James Webb Space Telescope has not just shown us pictures of the universe. It has shown us our place in it, our insignificance. With every new discovery, our ego shrinks a little more. We thought we understood the universe, but Webb has shown us that we have not even properly read the first page of the book. Those impossible galaxies, those prematurely formed black holes, those dark stars, and the mystery of the expanding universe, all of these are screaming that reality is far more frightening than we imagined. Perhaps H.P. Lovecraft was right. The oldest and strongest emotion of mankind is fear, and the greatest fear is of the unknown. James Webb has shone a torch into that unknown darkness, and the things staring back at us from there are challenging our physics, our logic, and our very existence. Asterisk, now the question is not what more will we discover. The question is whether we are ready to handle the truth that is coming. Because space is not silent. It was just waiting for us to be ready to listen. The universe is speaking, but its language is one of violence, of chaos, of scales and forces beyond our comprehension. Every piece of data Webb sends back is a sentence in that language. And the more we translate, the more disturbing the message becomes. We are not the center of creation. We are not the inevitable result of cosmic evolution. We are an accident, a fluke, a brief moment of complexity arising in a universe that is fundamentally hostile to our existence. Asterisk. Webb has revealed that the early universe was far more dynamic and violent than we imagined. Galaxies were forming and merging and tearing each other apart at a frantic pace. Black holes were devouring entire star-forming regions. Dark matter was clumping in ways we do not understand, creating structures that should not exist. And through it all, the expansion of space itself was accelerating, driven by some mysterious dark energy that makes up more than 2/3 of the universe, but which we cannot see, cannot touch, cannot understand. We live in a universe dominated by things we cannot observe directly. Dark matter and dark energy together make up 95% of everything, leaving normal matter, the stuff of stars and planets and people, as a tiny minority. Asterisk, the philosophical implications are profound. If we can only directly observe 5% of reality, how much can we really claim to know? How much can we trust our models and theories when they're built on such a narrow foundation? Webb is helping us observe more, pushing back the boundaries of the observable. But with every answer it provides, new questions emerge. The universe, it seems, is not just vast, but infinitely complex, with layers upon layers of structure and behavior that we are only beginning to glimpse. And the more we learn, the more we realize how much we do not know, how much we may never know, how much might be fundamentally unknowable. Asterisk, some of Webb's most disturbing observations relate to the cosmic web itself, the large-scale structure of the universe. We have known for decades that galaxies are not randomly distributed through space, but are arranged in a vast network of filaments and sheets, surrounding enormous voids where almost nothing exists. This cosmic web is thought to trace the distribution of dark matter, with normal matter falling into the dark matter's gravitational wells and forming galaxies along these filaments. Webb has been able to observe this structure forming in the early universe, watching as the first galaxies began to trace out these patterns. But what Webb has seen does not quite match what our simulations predicted. The cosmic web in the early universe appears to be more developed, more structured, more mature than it should be. It is as if someone hit the fast-forward button on cosmic evolution. The simulations, which are based on our best understanding of dark matter, dark energy, and gravity, predict a certain rate of structure formation. Reality, as observed by Webb, is outpacing those predictions. This could mean that dark matter interacts with itself or with normal matter more strongly than we thought. Or it could mean that our model of gravity needs modification. Or it could mean something else entirely, something we have not even considered yet. The cosmic web is the skeleton of the universe, the framework upon which everything else is built. If we do not understand how it forms and evolves, then we do not understand the universe at all. Asterisk Webb has also observed what astronomers call the epoch of reionization, the period when the first stars and galaxies formed and began, emitting ultraviolet light intense enough to ionize the hydrogen gas that filled the universe. Before reionization, the universe was opaque, filled with neutral hydrogen that absorbed ultraviolet light. After reionization, the universe became transparent, allowing light to travel freely through space. This transition is one of the most important events in cosmic history, marking the end of the cosmic dark ages and the beginning of the universe as we see it today. Webb was designed specifically to study this epoch, and it has provided stunning observations of galaxies from this era. Asterisk, but once again, what Webb has seen does not quite match expectations. The reionization process appears to have happened faster than models predicted. The first galaxies appear to have been more effective at producing ionizing radiation than we thought possible. And there are hints, still tentative but growing stronger with more observations, that reionization might not have been a smooth, uniform process, but rather patchy and chaotic, with some regions of the universe remaining neutral long after others had been ionized. This patchiness could have profound effects on the formation of the first galaxies and the evolution of the early universe. It suggests a level of complexity and dynamism that our current models do not capture. Asterisk, one of the most exciting and most unnerving aspects of Webb's mission is its ability to study the atmospheres of exoplanets. By observing planets as they transit in front of their host stars, Webb can analyze the starlight filtering through the planet's atmosphere and identify the chemical compounds present. This technique has already revealed the presence of water vapor, carbon dioxide, methane, and other molecules on distant worlds. These observations are bringing us closer than ever to answering the question of whether we are alone in the universe. But they are also revealing just how diverse and strange planetary atmospheres can be. Some planets have atmospheres made of vaporized rock. Others have clouds of molten iron raining down on their surfaces. Still, others have been completely stripped of their atmospheres by their stars' radiation, leaving behind bare, lifeless rocks. The search for biosignatures, chemical signs of life, in exoplanet atmospheres is one of Webb's key goals. The detection of certain combinations of gases, such as oxygen and methane together, which do not naturally coexist in equilibrium, and therefore suggest biological activity, would be strong evidence of life. But Webb has also taught us to be cautious. The chemistry of planetary atmospheres is incredibly complex, with many ways that abiotic processes can produce gases that might look like biosignatures. A planet with active volcanism might produce false positives. A planet with unusual atmospheric dynamics might concentrate gases in unexpected ways. Distinguishing true biosignatures from false alarms will require careful analysis and probably observations of multiple planets before we can confidently claim to have found life. Asterisk. And even if we do find biosignatures, what then? What kind of life might we be detecting? Will it be something recognizable based on the same fundamental chemistry as life on Earth? Or will it be something truly alien, using different molecules, different energy sources, different principles of organization? The universe is under no obligation to produce life that looks like us or thinks like us or communicates like us. We might find evidence of life but be unable to understand it, unable to communicate with it, unable even to recognize it as life at first. The philosophical and scientific challenges of making contact with extraterrestrial life, should we ever succeed, will be enormous. But the first step is detection, and Webb is bringing us closer to that milestone every day. Asterisk. Webb's observations have also shed light on one of the most mysterious phenomena in astrophysics: gamma-ray bursts. These are the most powerful explosions in the universe, releasing in a few seconds as much energy as the sun will emit over its entire lifetime. They come in two varieties: short bursts lasting less than 2 seconds, and long bursts lasting more than 2 seconds. Long bursts are thought to come from the collapse of massive stars into black holes, a hypernova event even more powerful than a typical supernova. Short bursts are thought to come from the merger of two neutron stars, or a neutron star and a black hole. Both types of events are incredibly violent, involving some of the most extreme physics in the universe. Asterisk. Webb has been able to observe the afterglows of several gamma-ray bursts, capturing infrared light emitted as the explosion interacts with surrounding material. These observations have revealed that gamma-ray bursts can forge enormous quantities of heavy elements, including gold and platinum. In fact, a single gamma-ray burst can produce more gold than the sun will produce in its entire lifetime. These explosions are cosmic forges, seeding the universe with the raw materials for planets and life. But they are also cosmic threats. If a gamma-ray burst were to occur close to Earth, with its beam pointed in our direction, the radiation would strip away our ozone layer and expose the surface to deadly ultraviolet light from the sun. Life on Earth would face a mass extinction event. Fortunately, gamma-ray bursts are rare, and the likelihood of one occurring nearby is low. But the fact that the universe contains such weapons of mass destruction, natural events that could sterilize entire planets, is a sobering reminder of our vulnerability. Asterisk. As Webb continues its mission, it will observe even more distant and more ancient parts of the universe. It will look for the signatures of the very first stars, sometimes called population 3 stars, which would have been made entirely of hydrogen and helium with no heavier elements. These stars, if they existed, would have been massive and short-lived, exploding as supernova and seeding the universe with the first heavy elements. Finding evidence of these stars would confirm a key prediction of cosmology and help us understand how the universe transitioned from its initial state to the rich, complex universe we see today. But as with everything else Webb has studied, there is no guarantee that what we find will match what we expect. The universe has a habit of surprising us, and every surprise is both thrilling and unsettling. Webb is also studying the centers of galaxies, including our own Milky Way, where supermassive black holes lurk. These monsters, millions or even billions of times more massive than the Sun, sit at the hearts of most large galaxies. Our own galaxy has one, a relatively quiet black hole called Sagittarius A star, with a mass of about 4 million suns. Most of the time it sits dormant, not actively feeding. But observations by Webb and other telescopes have caught it occasionally flickering, briefly brightening as it swallows a bit of gas or tears apart a passing star. Other galaxies have far more active black holes, actively feeding and growing, surrounded by accretion disks of superheated matter spiraling inward. These active galactic nuclei can outshine the entire galaxy. Visible across billions of light years, Webb has studied these active black holes in unprecedented detail, revealing the structure of their accretion disks, the jets of matter they shoot out at near light speed, and the effects they have on their host galaxies. These black holes are not just passive passengers, but active sculptors of galactic evolution. Their energy output can heat the gas in a galaxy, preventing it from cooling and forming new stars. This feedback mechanism is thought to be crucial in determining how massive a galaxy can grow. Without it, galaxies would continue forming stars until they ran out of gas, becoming far more massive than we observe. The black hole acts as a thermostat, regulating star formation and keeping the galaxy in balance. But this balance is delicate, and if it tips too far one way or the other, the results can be catastrophic. A galaxy can exhaust its gas supply and become a red, dead elliptical. Or it can undergo a burst of furious star formation that consumes all available material in a cosmic blink. One of Webb's most profound contributions may ultimately be philosophical rather than scientific. By revealing the universe in such stunning detail, by showing us its beauty and its terror, its complexity and its simplicity, its age and its violence, Webb is forcing us to confront our place in it. We are not the universe's purpose. We are not its center or its goal. We are a small, fragile phenomenon, arriving by chance on a small rocky planet orbiting an average star in an unremarkable galaxy in a universe filled with trillions of galaxies. Our existence is contingent, unlikely, temporary. The universe existed for billions of years before us, and will exist for trillions of years after us. Our sun will die, Earth will be consumed, our galaxy will merge with Andromeda. And eventually, in the far distant future, the last stars will flicker out and the universe will fade into a cold, dark heat death where nothing interesting can ever happen again. This cosmic perspective can be depressing, but it can also be liberating. If we are insignificant on a cosmic scale, then our problems, our conflicts, our petty differences are even more so. We are all inhabitants of a small blue dot, suspended in a sunbeam, the only home we have ever known. We should treat it and each other with care. The universe is vast and hostile, but we are here now able to observe it and ponder our place in it. That is a gift, a rare and precious gift. Webb is helping us appreciate that gift by showing us what lies beyond our small corner of existence. It is showing us wonders we never imagined and horrors we never wanted to face. It is expanding our horizons and humbling our pride. And perhaps most importantly, it is teaching us that the universe is not finished with us yet. There are more discoveries to come, more mysteries to solve, more questions to ask. The data Webb is gathering will keep astronomers busy for decades. Each observation spawns dozens of papers. Each discovery leads to new questions. The telescope's instruments are performing beyond expectations. Its mirrors are aligned perfectly, and its orbit at the second Lagrange point is stable. If all goes well, Webb could continue operating for 20 years or more, far beyond its original design lifetime. And in that time, it will revolutionize our understanding of the cosmos. It will see the first galaxies forming in the darkness after the Big Bang, It will watch stars being born and dying. It will analyze the atmospheres of dozens, perhaps hundreds of exoplanets. It will study the dynamics of our own solar system, from the weather on Jupiter to the composition of distant Kuiper Belt objects. It will observe supernovae, gamma ray bursts, colliding galaxies, and the cosmic web. It will, in short, be our eyes on the universe, seeing things we could never see from Earth and sending back knowledge that will transform how we understand reality. But beyond all the scientific discoveries, beyond the papers and the press releases and the stunning images, Webb is also a testament to human ingenuity and ambition. It took decades to design and build, involving thousands of engineers and scientists from around the world. It survived budget crises and technical setbacks and launch delays. And when it finally lifted off on Christmas Day 2021, the entire scientific community held its breath, knowing that if anything went wrong during the month-long deployment sequence, the entire mission would be lost. But everything worked. The mirrors unfolded perfectly. The sun shield deployed without a hitch. The instruments cooled to their operating temperature. And the first images, released in July 2022, were even better than anyone had hoped. Webb is a triumph of human collaboration, a symbol of what we can achieve when we work together toward a common goal. Asterisk, in a world often divided by conflict and competition, Webb stands as a reminder that we are all part of the same species, all inhabitants of the same small planet, all curious about the same vast universe. The questions Webb is answering are questions humans have asked since we first looked up at the stars. Where do we come from? Are we alone? What is our place in the cosmos? These are not just scientific questions, but philosophical and spiritual ones. They touch on the deepest aspects of human nature, our need to understand, our desire to connect, our fear of insignificance. Webb cannot answer all these questions, but it can provide data, evidence, facts that help us frame the questions more precisely and search for answers more effectively. And in doing so, it helps us understand not just the universe, but ourselves. Asterisk, as I think about Webb's mission and its discoveries, I am struck by the courage it takes to look into the darkness and see what is there. It would be easier, more comfortable, to stay ignorant, to accept the old models and the old assumptions and not question them. But that is not how science works. Science demands that we follow the evidence wherever it leads, even if it makes us uncomfortable, even if it challenges our cherished beliefs. Webb is a tool of that process, an instrument of discovery that does not care about our feelings or our preconceptions. It simply observes and reports. And sometimes what it reports is disturbing. The impossible galaxies, the premature black holes, the expanding tension, the rogue worlds, all of these are uncomfortable truths. But they are truths nonetheless, and we must grapple with them. We must revise our theories, update our models, expand our understanding. That is the nature of scientific progress. Asterisk, the universe James Webb is revealing to us is not the universe we expected. It is stranger, more violent, more mysterious, and more beautiful. It is a universe that contains wonders beyond imagination and horrors beyond comprehension. It is a universe that has existed for 13.8 billion years and will continue existing long after we are gone. It is a universe that does not care about us, that does not notice us, that will continue its grand cosmic dance whether we are here to observe it or not. And yet we are, against all odds, in defiance of entropy and chaos, we have arisen. We have built tools like Webb that allow us to see across billions of light years and billions of years of time. We have decoded the language of the cosmos and begun to read its history. We are, in a very real sense, the universe observing itself, a small part of the cosmos that has become conscious and curious. Asterisk, that is something worth celebrating, even as we confront the uncomfortable truths Webb is revealing. Yes, we are small. Yes, we are insignificant in the cosmic scheme. Yes, our existence is fragile and temporary, but we are also remarkable. We are also capable of understanding, of creativity, of love and wonder and curiosity. Those qualities may not matter to the universe at large, but they matter to us, and that is enough. Webb is not just showing us the universe. It is showing us ourselves, reflected in the cosmic mirror. And what we see there is both humbling and inspiring. We are part of something vast and ancient, something that began with the Big Bang and will end in ways we can only dimly imagine. But while we are here, while we have this brief moment of consciousness, we can look up at the stars and ask questions. We can build telescopes and space missions. We can explore and discover and learn. And that, perhaps, is the real message of Webb's mission. Not that we are insignificant, but that our significance is what we make of it. The universe may not care, but we do. And that makes all the difference. Asterisk, the revelations from Webb continued to pour in, each one more staggering than the last. As we process the data from this extraordinary machine, we are forced to confront not just scientific puzzles, but existential questions about the nature of reality itself. The telescope has become more than an instrument. It has become a mirror, held up to our understanding of existence, reflecting back not what we expected to see, but what is actually there. And the difference between those two things is profound and disturbing. Asterisk, one of the most perplexing discoveries Webb has made involves what astronomers are calling gravitationally lensed galaxies from the epoch of reionization. Gravitational lensing occurs when a massive object, like a galaxy cluster, bends the light. From objects behind it, acting like a cosmic magnifying glass, Webb has used this natural phenomenon to observe galaxies that would otherwise be too faint and distant to see. But what it has found behind these cosmic lenses has been deeply troubling. These magnified galaxies from the early universe show levels of chemical enrichment that should not exist. Heavy elements like carbon, oxygen, and nitrogen, which are only created inside stars and dispersed through supernova, are present in quantities that suggest multiple generations of stars have already lived and died. Asterisk. But how is this possible? When the universe is barely a few 100 million years old at this point, stars take time to form, time to live, and time to die. The first stars, made only of hydrogen and helium, should have been massive and short-lived, perhaps only a few million years from birth to supernova. But even accounting for rapid stellar evolution, the timescales do not work. To see the level of chemical enrichment Webb is observing, you would need not just one generation of stars, but several. And that should take at least a billion years, not a few 100 million. Yet, there it is, in spectrum after spectrum, undeniable evidence that the early universe was chemically mature far earlier than it should have been. Asterisk, some cosmologists have proposed that perhaps the very first stars were different from anything we see today. Perhaps they were supermassive, hundreds or even thousands of times more massive than our sun, burning through their fuel in just a few 100,000 years and exploding with such violence that they instantly enriched vast regions of space with heavy elements. These hypothetical objects, called population 3 stars, have never been directly observed. They would have existed only in the first few 100 million years after the Big Bang, and by now, they are long gone. But Webb might be seeing their fingerprints, the chemical signatures they left behind in the gas that formed the next generation of stars. If these supermassive first stars really existed, they would have been nothing like modern stars. They would have been fusion reactors of unimaginable power, their cores reaching temperatures and pressures that would make our sun look cold and gentle by comparison. Asterisk. The implications of these observations extend beyond just stellar evolution. They touch on the fundamental question of how structure forms in the universe. According to our current understanding, based on the Lambda's EDM model, structure formation is a bottom-up process. Small things form first, then merge to create larger things. Dark matter halos collapse first, then gas falls into them and forms stars. Then stars cluster into galaxies. Then galaxies merge to form larger galaxies and galaxy clusters. This hierarchical structure formation should be relatively slow, with massive structures taking billions of years to assemble. But Webb is showing us massive structures that assembled in just a few 100 million years. The timeline is too compressed, the process too rapid. Something is accelerating structure formation in the early universe, and we do not know what. Asterisk, one possibility that has gained traction in recent years is that dark matter itself might be more complex than we thought. The standard model of dark matter treats it as cold, meaning the particles move slowly compared to the speed of light, and collisionless, meaning the particles do not interact with each other except through gravity. But what if dark matter is actually self-interacting? What if dark matter particles can collide with each other, exchange energy, and even emit radiation? Just not radiation we can easily detect. Self-interacting dark matter could collapse more quickly than cold dark matter, forming dense halos that would more efficiently attract normal matter and trigger star formation. This would speed up structure formation and might explain why Webb is seeing such mature galaxies so early. But self-interacting dark matter raises its own problems. If dark matter can interact with itself, why don't we see evidence of that in the modern universe? Dark matter halos around nearby galaxies show no signs of the kind of heat and pressure that self-interaction would create. So either dark matter behaved differently in the early universe, which would be very strange, or we are misinterpreting Webb's observations, which seems increasingly unlikely given how consistent the data is. We are left with a puzzle that has no easy solution. A fundamental mismatch between theory and observation that will require either significant modifications to our models or genuinely new physics to resolve. Asterisk. Webb has also made unexpected discoveries closer to home within our own solar system. While most of its observing time is devoted to distant galaxies and exoplanets, Webb has occasionally turned its golden mirror toward the planets, moons, and asteroids that share our cosmic neighborhood. What it has found has been both fascinating and unsettling. Webb observed Jupiter's moon Europa, which is believed to harbor a subsurface ocean beneath its icy crust. Scientists have long suspected that Europa might be one of the best places in our solar system to search for life. The ocean, kept liquid by tidal heating from Jupiter's gravity, could provide the water, energy, and chemical nutrients necessary for life. Webb's infrared observations revealed plumes of water vapor erupting Europa's surface, confirming that the ocean below is in contact with the surface and suggesting that material from that ocean is being ejected into space. Asterisk. This is exciting because it means we could potentially sample Europa's ocean without having to land on the surface and drill through miles of ice. A spacecraft flying through one of these plumes could collect water droplets and analyze them for signs of life. But Webb's observations also revealed something unexpected. The water vapor in these plumes contains an unusually high concentration of salts and organic molecules, including some complex carbon compounds that on Earth associated with biological processes. Does this mean Europa has life? Not necessarily. These molecules can be produced by non-biological chemistry, but their presence, combined with the confirmed existence of a liquid water ocean and an energy source, makes Europa one of the most compelling targets in the search for life beyond Earth. Yet the same observations that excite astrobiologists also raise troubling questions. If Europa has life, what kind of life is it? The ocean on Europa has been isolated from the surface, from sunlight, from the rest of the solar system, for billions of years. Any life that evolved there would be completely adapted to that isolated, dark, high-pressure environment. It might be microbial, simple single-celled organisms clustered around hydrothermal vents on the ocean floor. Or it might be something more complex, ecosystems of strange alien organisms that have no analog on Earth. And if we ever send a mission to explore that ocean, what impact will we have? Will we contaminate Europa with Earth microbes, potentially wiping out an entire alien biosphere? Or will something from Europa contaminate us, a microbe or a virus so alien that our immune systems have no defense against it? Asterisk, these are not idle concerns. The history of exploration on Earth is filled with examples of biological exchange wreaking havoc. When European explorers reached the Americas, they brought diseases that decimated indigenous populations. When they explored the Pacific, they brought rats and pigs and plants that devastated island ecosystems. We must be extraordinarily careful as we venture into the oceans of Europa or Enceladus or any other potentially habitable world. The stakes are too high, the potential for irreversible harm too great. Webb's observations are guiding us toward these destinations. But they are also warning us to proceed with caution, to think carefully about the consequences of our actions, to recognize that in exploring these worlds, we are not just satisfying our curiosity, but potentially interfering with something precious and irreplaceable. Webb has also studied Saturn's moon Titan, the only moon in our solar system with a thick atmosphere. Titan is a world unlike any other, with lakes and rivers and rain, but instead of water, the liquid is methane and ethane. The surface temperature is a frigid negative 180 degrees Celsius, cold enough that water ice is as hard as rock. Titan's atmosphere is mostly nitrogen like Earth's, but it is filled with complex organic chemistry. Sunlight and charged particles from Saturn's magnetosphere break apart methane molecules in the upper atmosphere, and the fragments recombine to form a bewildering array of hydrocarbons and nitrogen-containing compounds. Some of these molecules rain down onto the surface, accumulating in layers of organic sludge that might be tens or hundreds of meters thick in some places. Webb's observations of Titan have revealed even more complex chemistry than we suspected. The telescope detected molecules that on Earth would be considered precursors to life, building blocks that could be assembled into amino acids, nucleotides and lipids, the fundamental components of living cells. Titan is like a natural laboratory for prebiotic chemistry, a place where we can watch the kinds of chemical reactions that might have occurred on Earth billions of years ago, before life began. But Titan is too cold for life as we know it. Chemical reactions happen slowly at such low temperatures, and liquid water, which is essential for terrestrial biochemistry, is absent. Any life on Titan would have to be based on completely different chemistry. Perhaps using liquid methane as a solvent instead of water. Perhaps using different molecules for information storage and metabolism. The possibility of such exotic life has tantalized scientists for years. Could there be methane-based life swimming in Titan's hydrocarbon lakes? Could there be organisms living in pockets of liquid water beneath the icy crust, where occasional impacts or cryovolcanism bring warmth? We do not know, and Webb cannot answer these questions directly. But it can map the distribution of organic molecules on Titan's surface. It can track changes in atmospheric composition, and it can provide context for future missions that will explore Titan more directly. NASA's Dragonfly mission, scheduled to launch in the late 2020s, will send a helicopter-like drone to fly around Titan, landing at multiple sites to study the surface chemistry and search for signs of life. Webb's observations are helping scientists choose where Dragonfly should go and what it should look for. But again, the same observations that inspire hope also inspire fear. Titan's organic-rich environment is both a potential habitat for alien life and a potential hazard. Those complex organic molecules, so abundant on Titan's surface, include many that are toxic or carcinogenic to terrestrial life. If we ever send humans to Titan, they will have to be extraordinarily careful not to come into contact with the surface materials. And if there's life on Titan, even microbial life, bringing it back to Earth for study could be catastrophic if it turned out to be harmful to terrestrial organisms. The same precautions that apply to Europa apply even more strongly to Titan. We are dealing with alien biochemistry, alien organisms, potentially alien pathogens. We must proceed with wisdom and restraint, balancing our desire to explore with our responsibility to protect both Earth and the worlds we visit. Webb's observations have also shed new light on the formation of our own solar system. By studying protoplanetary disks around young stars and nearby star-forming regions like the Orion Nebula, Webb is watching solar systems being born. These disks of gas and dust surrounding newborn stars are the raw material from which planets form. Over millions of years, dust grains stick together, forming pebbles, then boulders, then planetesimals, then planets. Webb can see this process in action, observing the gaps and rings in protoplanetary disks that indicate where planets are forming, tracking the movement of gas as it falls onto the young star or is blown away by stellar winds, measuring the composition of the disk material to understand what kinds of planets will form. Asterisk, what Webb has found is that planet formation is incredibly diverse. Some disks are massive and extended, with enough material to form dozens of giant planets. Others are small and depleted, barely enough material for a few rocky worlds. Some disks show clear signs of multiple planets already forming, with gaps and spiral structures carved by the gravitational influence of massive protoplanets. Others appear smooth and featureless, with no obvious signs of planet formation yet. This diversity tells us that planetary systems can turn out very differently depending on the initial conditions. The mass and composition of the disk, the environment around the young star, and pure chance. Our solar system with its 4 rocky inner planets, 4 giant outer planets, and a belt of asteroids and comets is just one possible outcome. Other stars might have dozens of small planets, or a few super-Earths, or giant planets that migrated inward to orbit close to their stars, or no planets at all. Webb has also observed the process of photoevaporation, where ultraviolet light from nearby massive stars heats and disperses protoplanetary disks before planets can fully form. In dense star-forming regions, where thousands of stars are born close together, the intense radiation from the most massive stars can destroy the disks around smaller stars, preventing planet formation entirely. This means that the birthplace of a star can determine whether it will have planets. Stars born in isolation or in small groups are more likely to form planetary systems, while stars born in massive clusters might be stripped of their planet-forming material before the process can complete. This has profound implications for the prevalence of planets, and therefore potentially life, in the galaxy. If a significant fraction of stars are born in environments hostile to planet formation, then planets might be less common than we think. Asterisk. One of the most philosophically challenging aspects of Webb's discoveries is what they reveal about time itself. When we look at distant galaxies, we are not seeing them as they are now, but as they were billions of years ago. When the light we are observing left them, those galaxies have continued evolving since then. Some might have merged with other galaxies. Some might have exhausted their gas supply and stopped forming stars. Some might have been torn apart by tidal forces or consumed by other galaxies. The universe we see through Webb is a museum of the past, filled with objects that no longer exist in the form we observe them. And yet, this is the only way we can study the early universe. We cannot travel back in time. We can only observe the light that has been traveling through space for billions of years, finally reaching us now. Asterisk. This creates a strange disconnect between observation and reality. When we see a galaxy that existed 13 billion years ago, we are seeing something that is, in a very real sense, no longer there. If we could somehow instantaneously teleport to the location of that galaxy, what would we find? Would it still be recognizable? Would it have merged with others to form a massive elliptical? Would it have evolved into something like our own Milky Way? We cannot know. The light carrying information about what happened next has not reached us yet, and will not reach us for billions of years. We are trapped in our own light cone, able to see only the past of distant objects, forever cut off from their present. Asterisk. This temporal disconnect becomes even more pronounced when we consider the expansion of the universe. The galaxies Webb observes are not just far away, but receding from us as space itself expands. The most distant galaxies are receding faster than the speed of light, not because they are moving through space faster than light, which would violate relativity, but because the space between us and them is expanding. This means that light from the most distant galaxies has been stretched by the expansion, shifting it from visible light to infrared light, which is why Webb's infrared vision is so crucial. But it also means that there are parts of the universe we will never be able to see. Regions so distant that their light will never reach us before the universe expands too much. There is a cosmic horizon beyond which the universe is forever invisible to us. This realization is humbling and isolating. The universe is larger than the observable universe, perhaps infinitely larger, and we are confined to our small patch, able to see only a fraction of what exists, and that fraction is shrinking. As the universe continues to expand and the expansion accelerates, more and more galaxies will cross the cosmic horizon and disappear from view. Billions of years from now, observers in our galaxy will look out and see far fewer galaxies than we see today. Eventually, if the expansion continues indefinitely, our galaxy and its nearest neighbors will be alone in an observable universe that appears empty, surrounded by darkness in all directions. Future astronomers, if they exist, will have no direct evidence that the Big Bang ever occurred. No cosmic microwave background to study, no distant galaxies to observe. They will have to deduce the history of the universe from local observations alone. A far more difficult task. This scenario, sometimes called the Big Chill or heat death, is the most likely fate of our universe according to current observations. The expansion will continue, accelerating under the influence of dark energy, until all the stars burn out, all the black holes evaporate through Hawking radiation, and the universe becomes a cold, dark, empty expanse where nothing interesting can ever happen again. This will take an unimaginably long time, far longer than the current age of the universe, but it is where we are headed. Unless something changes, unless dark energy behaves differently than we think, unless there is some new physics that intervenes, this is the ultimate destiny of everything. It is a bleak vision, made all the more disturbing by Webb's observations confirming that the expansion really is accelerating and that dark energy really does dominate the universe's future. But perhaps there is hope. Perhaps our understanding of dark energy is incomplete. Perhaps it is not a constant, unchanging force, but something that varies over time. Some models of dark energy, particularly those involving fields similar to the inflaton field, thought to drive cosmic inflation in the first moments after the Big Bang, predict that dark energy could decay or change its properties. If dark energy were to weaken in the future, the expansion could slow down or even reverse, leading to a big crunch where the universe collapses back on itself. Or dark energy could strengthen, leading to a big rip where the expansion accelerates so rapidly that even atoms are torn apart. Neither outcome is comforting, but they are at least different from the slow, cold fade of the heat death scenario. Webb cannot tell us which future awaits the universe. Its observations cover only the tiniest fraction of cosmic time. A few billion years out of a history that spans nearly 14 billion years, and a future that could last trillions or more. But it can measure the current behavior of dark energy, tracking how it has changed over the history of the universe. And those measurements can help constrain the models. If we are very lucky, and if we are very clever, we might be able to figure out what dark energy is, and what it will do in the future. That knowledge will not save us from the ultimate fate of the universe, but it will at least give us some certainty, some understanding of where we are going and why one of the most unexpected contributions Webb has made is in the field of gravitational waves. Although Webb is not designed to detect gravitational waves directly, it has observed the electromagnetic counterparts of gravitational wave events detected by ground-based observatories like LIGO and Virgo. When two black holes or neutron stars merge, they emit gravitational waves, ripples in space-time that can be detected as they pass through Earth, but in some cases, particularly neutron star mergers, the event also produces electromagnetic radiation, light that can be observed by telescopes like Webb. By observing these events in both gravitational waves and light, astronomers can learn far more than they could from either signal alone. Webb has observed the aftermath of neutron star mergers, capturing the glow of the kilonova, the explosion that occurs when two neutron stars collide and merge. These events are thought to be the primary source of heavy elements like gold, platinum, and uranium in the universe. The collision creates such extreme conditions, with temperatures and densities beyond anything found in normal stars, that nuclear reactions can build up the heaviest elements in the periodic table. Webb's observations have confirmed this, detecting spectral signatures of these heavy elements in kilonova light. But they have also raised new questions. The amount of heavy elements produced seems to vary widely from event to event. Some kilonovae are rich in heavy elements, while others produce relatively little. Why this variation exists is not clear. It might depend on the masses of the neutron stars, the angle at which they collide, or the properties of the dense matter inside neutron stars, which we still do not fully understand. Asterisk neutron stars are among the most extreme objects in the universe, packing more mass than the sun into a sphere just 20 kilometers across. The matter inside them is compressed to densities beyond anything achievable in laboratories, crushed so tightly that atomic nuclei merge and dissolve, forming a soup of neutrons and exotic particles. The physics governing this matter is uncertain. Different models predict different behaviors, different equations of state for neutron star material. By observing how neutron stars behave when they merge, Webb and gravitational wave observatories are providing the only experimental tests of this ultra-dense matter. Every kilonova observed, every gravitational wave signal analyzed, helps narrow down the possibilities and brings us closer to understanding the fundamental nature of matter under extreme conditions. But once again, these observations also reveal the violence of the universe. Neutron star mergers are catastrophic events, releasing as much energy in a few seconds as the sun will emit over its entire lifetime. If a neutron star merger occurred within a few thousand light years of Earth, the radiation would be lethal, sterilizing the surface and potentially stripping away our atmosphere. Fortunately, such events are rare, and the nearest neutron stars are far enough away that we are safe. But it is a reminder that the universe is filled with dangers, with events of unimaginable power occurring regularly on cosmic scales. We live in a fragile bubble of safety, protected by distance and by luck. That bubble could burst at any time. Asterisk Webb has also contributed to our understanding of cosmic inflation. The theory that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation explains many features of the universe, including why it is so uniform and flat, and why distant regions that should never have been in contact appear to have the same properties. But inflation is still a theoretical idea, supported by evidence but not yet proven. One prediction of inflation is that it should have produced gravitational waves, and those gravitational waves should have left an imprint on the cosmic microwave, background radiation in the form of a specific pattern of polarization called B-mode polarization. Detecting this B-mode polarization would be smoking gun evidence for inflation. Asterisk. Webb is not designed to measure the cosmic microwave background directly, but its observations of the early universe can test other predictions of inflation. Inflation predicts that the initial density fluctuations in the universe, the tiny variations that seeded the formation of all structure, should follow a specific statistical pattern. By measuring the distribution of galaxies in the early universe, Webb can check whether this pattern matches what inflation predicts. So far, the match appears to be good, supporting the inflationary model. But there are competing theories, alternatives to inflation, that make different predictions. And distinguishing between them will require even more precise observations. Asterisk. One of the most intriguing alternatives to inflation is the cyclic model, which proposes that the Big Bang was not the beginning of the universe, but just one event in an endless cycle of expansion and contraction. According to this model, the universe has existed forever, undergoing repeated cycles of Big Bang, expansion, contraction, and big crunch, each cycle seeding the next. The cyclic model can explain many of the same features as inflation, but it makes different predictions about the very early universe and the nature of the Big Bang, Webb's observations of the earliest galaxies and the structure of the early universe could potentially distinguish between these models, providing evidence for one over the other. But so far, the data is not conclusive. Both inflation and cyclic models remain viable, and we may need observations beyond Webb's capabilities to settle the question. Asterisk. The philosophical implications of these competing models are profound. If inflation is correct, then the Big Bang was the true beginning, the moment when time and space came into existence. Before the Big Bang, there was nothing, not even time. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question is meaningless. But if the cyclic model is correct, then the Big Bang was not the beginning, but merely a transition, one event in an eternal sequence. The universe has always existed and always will exist, cycling through different phases, never truly beginning or ending. This would mean that time is infinite, that the universe has no ultimate origin, and that our cosmic history extends infinitely far into the past. Asterisk, which model is correct? We do not know. Webb is providing clues, hints, pieces of evidence, but the full picture remains elusive. And perhaps that is fitting. The universe is under no obligation to make itself easily understandable to us. It is vast and complex and ancient, operating according to laws we are still struggling to comprehend. Every answer Webb provides raises new questions. Every mystery solved reveals deeper mysteries beneath. We are like children exploring a vast mansion, opening door after door, finding wonders and horrors in equal measure. Never quite sure what lies behind the next door or whether we will ever reach the end of the hallway. Asterisk. As I think about all that Webb has revealed and all that it suggests, I am struck by a sense of awe mixed with unease. We are privileged to live in an age when such observations are possible, when we can peer billions of light years into space and billions of years into time, when we can watch galaxies forming and stars dying and black holes feeding. But we are also burdened with the knowledge those observations bring. The uncomfortable truths about our insignificance, our vulnerability, our limited understanding. We are cosmic spectators, watching a drama unfold on scales we can barely comprehend, knowing that we are part of that drama but unable to control our role in it. Asterisk. The universe James Webb is revealing is not the orderly, comprehensible, manageable universe we might have hoped for. It is wild and chaotic and violent, governed by forces we do not fully understand, filled with objects that defy our expectations and challenge our theories. It is a universe that began in a moment of unimaginable violence and has been expanding and evolving ever since, creating stars and galaxies and planets and on at least one small world, life and intelligence. It is a universe that will continue long after we are gone, indifferent to our existence, uncaring about our fate. And yet, it is our universe, the only one we have, the only one we will ever know. We are part of it, made of it, born from the ashes of ancient stars, and destined to return to those ashes when our time is done. Asterisk. Webb is teaching us to see the universe as it truly is, not as we wish it to be. That lesson is sometimes beautiful and sometimes terrifying, but it is always worth learning. For in understanding the universe, we come to understand ourselves, our origins, our nature, our possibilities, and our limitations. We are the universe made conscious, a small part of the cosmos that has awakened and begun to contemplate its own existence. That is a remarkable thing, perhaps the most remarkable thing in all of existence. And whatever the universe throws at us, whatever mysteries and challenges and horrors await us in the darkness between the stars, we can face them with the knowledge that we are trying, we are learning, we are growing. We are reaching out into the cosmos, driven by curiosity and wonder, seeking answers to questions as old as humanity itself. And in that reaching, in that seeking, we find meaning and purpose and connection to something far greater than ourselves. Asterisk. The James Webb Space Telescope is more than a machine. It is an extension of human consciousness, a golden eye we have placed in the heavens to see what we cannot see with our own eyes, to reach what we cannot reach with our own hands. Every image it captures, every spectrum it records, every piece of data it sends back is a gift, a glimpse of the infinite, a reminder of how far we have come and how far we have yet to go. We stand on the shoulders of giants, the scientists and engineers and dreamers who made Webb possible, and we look out at a universe that is stranger and more wonderful than any of them could have imagined. And though that universe may be indifferent to us, though it may contain dangers we cannot yet comprehend, though it may ultimately defeat all our efforts to understand it, we will keep looking, keep questioning, keep reaching out into the darkness, because that is what we do. That is who we are. We are explorers, seekers, questioners. We are human. And the universe, vast and terrible and beautiful, is ours to discover.